Okay. Since I've got some practice now calculating Taylor series, I'm going to put this to work and try to build up approximations of certain functions. One of the very nice things about the Taylor series is that it comes with the Taylor series remainder formula. I can estimate how far off a partial sum of the Taylor series is going to be from the actual value of my function. And the nice thing about that is that if I start my Taylor series and only go out a certain number of terms, what I've got then is a polynomial. And what more could you ask for than just have a nice polynomial to represent your function, even if it's slightly off. So for all of these problems, I'll be using the same margin of error. I want to have the correct value of my functions plus or minus 0.01 or 1/100th. So the absolute error is going to be at most 0.01. For this first problem, I'm looking at the sine function, and I've got sine of x over 4. When I make a Taylor series approximation, when I make a Taylor polynomial, I need to specify what values of x I'm interested in. So for this problem, I'm going to be looking at x between negative pi and pi. My approximation can do whatever it wants outside of those bounds. I just want it to be accurate inside this interval. So the remainder formula for the Taylor series says that my error for this problem is going to depend on a couple different things. The first of them is the centering value. Now, it's typical in this kind of work that since I'm working on a finite interval, I'm going to center my Taylor polynomial in the center of the interval. So here that's going to be the number 0. Now, my error is going to be determined by the derivative of my function. So I need to know what the number n plus 1 derivative of my function is, and I need to evaluate that at z. Now, z is an unknown number. Z is some number between x and the center value for this series, which is, again, 0, which does make the Taylor remainder formula a little bit tricky to work with. Then I will multiply the value of this derivative by x minus a to the power n plus 1. Here my a is the number 0. This is all divided then by the number n plus 1 factorial. So this fraction here gives me an upper bound on the error. Now, the way that I can make this easier to work with, well, for one, I only care about the magnitude of this quantity. These lines are getting in the way now. I only care about the magnitude of this quantity. So I'm going to put everything in absolute value bars. More than that, though, I can make the formula easier to work with by overestimating the quantities that I see. For example, I know that I only care about values of x up to the number pi. So the very largest that this term in parentheses here can be is pi, which tells me that my fraction is always going to be less than this other fraction where I've replaced x to the power n plus 1 by pi to the power n plus 1 instead. I'm going to keep the factorial in the denominator. Factorial functions grow very quickly, and so that will help me keep the error term small. Now the question is, what do I do about that sine function? I'm supposed to take its derivatives. Well, let's think about what those derivatives are. The 0th derivative of this function is sine of x over 4. I've taken 0 derivatives, the function remains unchanged. To take the first derivative of this function, I'll have the cosine of x over 4, and then I need to multiply by the derivative of what's inside. I need to use the chain rule. So this will be cosine of x over 4 times 1/4. Okay, let's keep going. My second derivative will be minus the sine of x over 4 times the number, well, 1/4 squared, so 1 over 16. My third derivative is going to be minus cosine of x over 4 times 1 over 64. I'm starting to see a pattern. I'll always have one of the basic trig functions, plus or minus sine, or plus or minus cosine. And they'll always be evaluated to the number x over 4. Excuse me, that should say times. When I get back to, that should say times. There we go. These will always be multiplied by a fraction whose denominator is 4 raised to a power. What power is that? The power is the same as the number of derivatives we've taken. Every derivative gives me an extra power of 1/4. Again, I'm going to make this simpler by overestimating. I know that the sine function is always a number less than or equal to 1. I know the cosine function is always a number less than or equal to 1. But then I got to multiply by 1/4. I know that minus the sine function is always a number less than or equal to 1, but I got to multiply by 1/16. I know that minus the cosine is going to always be a number less than 1, but then I have to multiply by 1/64. So in my overestimates, I can replace this derivative by the number 1 over 4 to the power n plus 1. So I'm going to use this fraction here to do my estimation. If I can get this fraction less than my margin of error, I'm all set. Now, I've set Desmos up here to have a slider for a variable n. So I'm just going to type in the formula. I want 1 over 4 to the power n plus 1. This is going to be multiplied by pi to the power n plus 1. Then everything I see is going to be divided by n plus 1 factorial. So Desmos has chosen to write this a little bit differently than I said it, but everything seems to check out. And the nice thing about the slider is I can just change the value of n. So right now n is 0. And this is telling me that my error could be as large as 0.78. Well, that's too big. I want my margin of error to be smaller, so let's increase the n and see if I can get the error more under control. So if n equals 1, the amount of error that I could have, it might be as large as 0.3. That's still too big, so I'm going to look at the next value of n. If n equals 2, my error might be as large as 0.08. So this is a good trend. My error is getting smaller each time. but still not as small as I want it to be. So let's try n equals 3. Very close. We've got error that could be as much as 0.015. So I think at n equals 4, we should have this. N equals 4, we'll have 0.002. That's the largest our error could be for using the degree 4 Taylor polynomial. And that's within my tolerance here. That's within my desired margin of error. So what I've done now is I've determined that the degree 4 Taylor polynomial will be good enough to approximate the function as with the error to be less than 0.01. It'll happen to be better than that, which is nice. So let's actually figure out what that Taylor series is supposed to look like so we can get our approximation. The general formula for the Taylor series says I take the sum from n equals 0 to infinity. Desmos won't be able to calculate this infinite sum for me, but I'll at least use it to make the formula look neat. I want to take the nth derivative of my function, evaluate that at my center value, which here is 0. And I'll take x minus 0 and raise that all to the power n. And this all gets divided by the number n factorial. Okay. Well, I know what these derivatives are, so I can figure out what my coefficient should be, and I can stop when I get to the 4th power here. So I'm going to turn my guides back on. And remember, I only want the approximation to be valid from minus pi to pi. Whatever it does outside of these, I don't care. And what I'm going to do is I'm going to start writing out the terms of my Taylor series. So the constant term, I'll take the original function, sine of x over 4, and I'll plug in 0. Well, sine of 0 is 0, so my constant term is 0. Then I'm going to add on the linear term. The linear term uses the first derivative, which I know is cosine of x over 4 times a quarter. I wrote that earlier, but I've since erased that. Cosine of 0 is equal to 1, so my coefficient here will be 1/4 times x to the power 1. And I'm supposed to divide by 1 factorial, which I already know is 1, but there's the formula. So this is my degree 1 Taylor polynomial. And it's actually already doing a pretty good job of approximation here. But from my earlier calculation, I know that it's not going to have the margin of error that I wanted. So notice at the far right side here, the error is at its worst. In red is the actual value of the function, 0.707. And in green is the value of the approximation. I get pi over 4. Well, what is the difference between those things? Pi over 4 minus 0.707. Well, that's an error of 0.07. That's still too much error for my tastes, just like my formula predicted. So I'll have to add on the degree 2 term. My coefficient is going to be coming from the second derivative of this function, which again is minus the sine of pi over 4 times 1/16. Now I know that sine of 0 is 0, so this will end up being 0x squared. And I'll keep going. I'll do my cubic term For the third derivative of this function, I got minus the cosine of x on 4 all times 1/64. So I put in my 0. Negative cosine of 0 is -1. So this will be minus. And I've got 1/64 from the coefficient. I'll have x to the power 3. And that's looking a bit weird so far. But, oh, right, I need to divide by that factorial number. So here I'm dividing by 3 factorial. All right, that's looking much better. I have fixed the error that I was seeing before. So this right here is my degree 3 Taylor polynomial. Now something funny happens in this problem because my fourth term, well, my fourth derivative of this function will be back to the sine function times 1/256. But I know that's going to be 0 when I plug in x equals 0. So my fourth power term doesn't really do a whole lot for me in terms of approximation. Nevertheless, these 5 terms give me my degree 4 Taylor polynomial. It happens to have leading term 0, so it's really a cubic polynomial. That can happen occasionally. But this approximation stays within my margin of error for the whole interval. In fact, at this level of zoom, it's very difficult to distinguish the two functions from each other. Remember, the very most that the green curve and the red curve behind it could differ by is 0.02. And it's only outside of this interval that the estimate can get away from the actual value of the function.